All right, welcome everybody to Colin Chandler's thesis defense. All right, so I don't know if you all know who Colin Chandler is, Colin Orion Chandler, but I just wanted to go through this briefly in case some of you might be familiar, might not be familiar. What's that?
Are you on Zoom sharing?
I'm not on Zoom sharing. Should I? Oh. Thank you. No, I can do
this camera. Oh, you got it. All right.
1 minute. Hybrid. What's the password?
Orion, lowercase. Now everyone knows.
Okay. Join computer audio. Hold on. It's weird seeing myself.
I let people turn their video on. That's not good.
Host is disabled participant screen sharing. Hold on. How do I? Oh, you have to make me a.
Yes, you're publishing.
You have to share my screen.
Right, but I said enable sharing, so now
anyone
can share of the power with this picture here. What could go on?
All right. I think it's on Zoom. Hopefully there's not horrible feedback, but I won't know. Okay, who is Colin Chandler? Colin Orion Chandler. You might not know. Professionally, pretty standard, although very good. BS in astrophysics from San Francisco State University, graduate cum laude and honors, president of the SFSU Astronomy Club at the time, came to NAU in 2016. Presidential fellowship from our president, Rita Cheng, 2018 NASA GRFP fellow, 2021 outstanding graduate teaching assistant. LSST early career representative. That's one of the many things he's done. And he already has 5 first author peer-reviewed papers. Very good. But I don't know if that really tells us who Colin is. However, there is this this public outreach thing that LSST has been doing. They actually came up with a trading card for Colin, among other people, I assume. Planetary scientist. He has this quote, "Be persistent, maybe to the point of being stubborn," which I think is pretty accurate for Colin. And highlights he co-founded an IT consulting company. That's what he did before he came to NAU. And he majored in Japanese before switching to physics. Studies active asteroids, which I'm sure I'll tell you about. But we still don't know who is he, and more importantly, with the trading card, you want to know whether you trade or not, right? Like, what are his stats? Like, do I trade Colin for Will Grundy or David Trilling? I don't really know without some stats. So I figured, well, I don't know if there's a LSST stats, but I figured we could do a little D&D stats here. So Dungeons and Dragons, a lot of stats there. So I filled out some things there. Ranger level 3, human lawful good, 16 intelligence, 1 hit point down. I think you've been working pretty hard. So, but what we really want to know is these things on the right, the personality traits, ideals, bonds, that tells you what a person is. Okay, so here they are. Okay, personality traits, persistent to the point of being stubborn, intermediate level Japanese, master in high performance computing, not a master like a degree, he's just a master, maybe a guru, and he's really into outdoor sports. I don't know if you know about his outdoor achievements. All right, there we go. So you can see him snowboarding there in the middle. On the left, he's trying to learn to ski. The middle bottom, gravel biking. Upper right, he's kayaking with Mark. Upper left, he's Nordic skiing, and lower right, he's scraping ice off the Vatican Advanced Technology Telescope, also called the VAT, which we'll talk about later. But actually, before he was going, so the upper left, he's actually going to the VAT, which is about a 7-hour drive, and it had just snowed, so we decided to ski around Lake Mary. Why not? I'm passing by Lake Mary anyway. I have my skis in the car. I'll just ski around Lake Mary. So, over 10 miles, 12, 14, how far is it? I don't know. It's very long. Anyway, so he did that. That's the kind of stuff he does. Okay, so outdoor sports. What about these ideals? Attention to detail, definitely. We'll never use Helvetica font. Horrible font. It's actually owned by somebody, so technically you could probably have to pay someone, and it looks terrible. Like in Helvetica, the L is kind of off to the, it's closer to the V than the E. The F and the T are different like heights. It's just a horrible font. What about his bonds? General class amateur radio operator, really likes Spider-Man. So I didn't really notice he didn't tell me this outright, but I kind of deduced it. There he is at the vat in the operating room, dressed in a Spider-Man costume. I don't know who that alien person is. And I thought, okay, so he's got a Spider-Man costume, it's Halloween, you know, whatever. But then I saw this picture on Strava. So also a Spider-Man costume, Nordic skiing at the Nordic Center. And you can notice it's two different costumes, right? The spider is black in the first one and it's white in the other. So he owns more than one Spider-Man costume. Probably more than two, I'm guessing. Okay, really like Spider-Man. What about the flaws? Cannot function without artisanal coffee. So at the Vatican telescope, he actually brought this huge thing, like bigger than a bread box coffee machine. What was it called again? I forget the name. Okay, anyway, but really nice coffee machine. There was two other coffee machines there, like a drip one and like the pod one, but that wasn't good enough. He had to have the artisanal coffee, which I really appreciate. Actually, it was really good. Also, the last flaw, I couldn't come up with more than two. Musophobia, which is fear of mice and rats, which we also found out at the Vatican telescope. There was an infestation that was coming, and I woke up with like signs of mice in my bed one morning. And then I left, not because of that, I was scheduled to leave anyway. And then Will Oldroyd came in. And so the two of them were there during this mouse infestation. And I know Colin really didn't like mice because I'd be talking, when I was there, I was talking to him and I'd be like, oh, there's one behind you. And he'd be like, ah, you know, so very, very frightened of mice and rats. So actually Will and Colin went to the large binocular telescope next door and slept there for the remainder of the run to avoid the mice, at least during the time they were asleep. All right, so that's Colin. That's it. Now, I think Colin's going to tell you about active asteroids.
Thanks for that, Chad.
Colin, this is Ty. Am I coming through?
Hey, Ty.
Can we confirm that David Trilling is in the room? We need to do that for official purposes.
Oh, more?
David Trilling is in this room. You can hear him asking about lights.
That's pretty.
Okay, thanks, Colin.
Thank you.
But now we can't see the bottom screen. That's not bad. What did we do before?
It's on scale, but I think it's fine.
Oh, that's good. Is that too? Is that okay? Now you can see the pizza, but you can't see Colin. Or this one doesn't have a dimmer, unfortunately. So can you see those screens? Yeah, those screens are fine. Okay, because they're just really bright.
David, can you yell loudly that you're here so Ty can hear you for official purposes?
Hi.
There you go.
Perfect.
Just that?
I don't know. No, it's fine. Can people hear me in the back? Yes, great. Louder. Oh,
I don't know if the mic's oh, maybe you have to move that.
How about now? Did that change anything?
I don't know if the mic is on.
It's got a green light.
You tap it.
Just drag all these up. Did that do anything? No? Okay.
Tap it.
Tap the mic.
Oh, just put it on your in the middle.
That's more buttons.
Like below the button. No, you can just put it below the button. It doesn't have to be that close to your face.
How about that? Okay.
Just put it there.
Right there.
Yeah.
Wow. This is it's 1:15. Just gonna throw that out there. Okay. It's fine.
Right.
Only the best here. Very professional. Can you hear me in the back? Yes. This is just saying yes. Okay. Hi, everyone. I'm, as Chad so nicely introduced, Colin Orion Chandler. I'm going to talk to you about my dissertation entitled Chasing Tails, Active Asteroid Discovery with Astrophymatics and Citizen Science. My committee is composed of Chad, the chair, David Trilling, Henry Shea, Jonathan Fortney, Mike Downlock, and Ty Robinson, all of whom are online, except for David and Chad. And then also thanks Laura Bonds from the Brad Colleges, our external rep. So just a quick outline, we're going to talk about, well, about me. I don't think we need that anymore. And then motivation for why I'm doing what I'm doing. Some milestones along the way. I'm going to introduce this citizen science project I've got and define what that even is. And then some teasers for some up and coming papers and discoveries that are happening, and a quick summary.
Please share screen.
Thank you, Mark. Let's try that again. Yeah, all right. Can you see on Zoom?
Yes.
Yes.
Thank you. All right, there we go. So about me, okay, you heard about a lot of other things like wearing Spider-Man costume at the vat. This is me standing on the vat with the large binocular telescope in the background and the sub-millimeter telescope. So I'm going to talk about unusual active solar system bodies. So not just active asteroids, but also active centaurs and some other things. That's what this talk is about. I also do some work on exoplanet atmospheres. And as Chad said, I like astroinformatics and high performance computing, which is a fancy way of saying big data and supercomputers. And then for the modes, I like archival data. I really like finding new science out of existing data that's online and also observing at telescopes. Some other random things I've done here, there's way too many to list, but an Oumuamua paper that David led, and double asteroid redirection test, which is this mission that's going to go and smack the moon of an asteroid and see what happens. That was with Christina Thomas, Bill Oldroyd, Chad Trujillo here. And binary TNO with I'm doing this paper with Bo Grundy, who's also here, and Chad and Will Oldroyd. So let's get right to the motivation for what I'm doing. And the main word is volatiles. So these are ices like carbon dioxide or water. Water is actually a more interesting one. And we don't really know where they are in the solar system right now exactly, and we also don't really know the origin of them on Earth. So this little diagram shows the early solar system. There's comets, there's Jupiter in the front, and there's some things hitting. And what is that? So the comets, we were a long time, that's the spot where a lot of water came from. There's not a lot of agreement, but maybe 10% is kind of a favorite number right now for how much water on Earth came from comets. Definitely depends on who you ask. Another one is accretion, so that some water came with the place, was born with the planet, and then also that some was delivered maybe by asteroids. And depending on who you ask, if you're biased like me, it's 90%, but it depends on who you ask. So what are these other objects to where volatiles could come from? So that's sort of fundamental questions of where's water now and where did it come from? And volatiles also have utility. For example, from water you can get fuel, power, air, and water, obviously, and this is important for future space exploration, also asteroid mining. Chad just pointed out there's probably rubble piles, and so as soon as that thing moves, it's just going to all break apart, but we're going to ignore that. It's a cool graphic. Tidbit for the day, it takes as much fuel to get from Earth to Earth's orbit as it takes to get from Earth's orbit to Mars and basically anywhere. So another nice thing is if we could actually make fuel at some point in space, it would make space travel a little bit more sustainable, environmentally friendly, cost effective, and all that stuff. No more. Yeah, there's a way to do that, isn't there? That one, there we go. Better?
It's still there. Click that next.
Oh, this is a multi-screen. On?
Yes.
All right, cool. It's interesting, 3 different things. So layout of the solar system, just as a recap, these are not to scale in terms of the distance. They are supposed to be scaled in terms of their size. So starting from the sun at the left, moving through some planets. There's Ceres that's an asteroid belt between Mars and Jupiter. That's not the only thing in the asteroid belt, but that's the only one in this picture. The gas giants, Jupiter and Saturn, some ice giants, Uranus and Neptune, and then Pluto and Charon, Eris and Senda. Trans-Neptunian objects, things that are from the Kuiper belt, which is like 30 AU, or the orbit of Neptune on to about 50. And then just to describe where volatiles are. So we mentioned comets earlier, they're kind of found all over the place. Asteroids have some. This is Ceres right there with a little white spot that's thought to be volatiles. I know I'm in FlagSat, I should put this at TNO, but it's the only thing that has a cool picture out there. So it's there with ice, and it's gorgeous. The last one that we need to talk about is centaurs. These are objects that orbit between the orbits of Jupiter and Neptune. There are like 6 conflicting definitions for centaurs out there, but this is a pretty widely adopted one, so we're going with that. So yeah, that's the balance for centaurs right there. So another reminder just about comets and how we classify things. Comets were the first minor planets known. They were seen by people for thousands of years with petroglyphs, and so they're identified visually, and that's still the gold standard today for identifying activity. This is showing a silk scroll from 200 BC in China, and this has got multiple corroborating scrolls, which I think is great about our field. We have this kind of history. However, in more recent times, we do a lot of orbital classification of objects, and so that's what's shown on the right here. These are a handful of different comets, Hyakutake and some others, famous Halley, and just how different some of those orbits can be, but they do have different dynamical classifications. And so this is just an important distinction. I'll say the phrase class of objects, and it's not, I usually refer to comets as being both dynamically and visually active. I think you should have both personally. So I like to show this slide and ask who thinks which one is an asteroid and which one is a comet? I mean, it's kind of loaded because you came to this talk, so you know the title already. But this one, on the one with the giant tail, that's Active Asteroid P2013 R3. And this beautiful comet Temple 1 doesn't look like it's outgassing a lot. It did once we hit it, but it's if you were just to look at these two and you were only going by visual classification, you might be a little confused. So continuing this blurring these lines between comet and asteroid really started in 1949 with the discovery of the first active asteroid known, which is 4015 Wilson-Harrington. And this is actually plate, the ESO scan, which I was really stoked about. And so this is the first discovery on the left there. There wasn't another visual identification though for something like 40 years after this. So really the active asteroids that we talk about today are actually all really recent discoveries. And the most recent one is shown on the right there. That's 2005 Q173. That's an image from Shea et al. 2021. So in general, they're pretty rare. There's fewer than 30 known. Depends on how you classify it exactly, but even with 30, that's not very many in order to make broad statements about them. So we want to find more of these objects. Active centaurs, this is the other body I mentioned earlier. So there's these are even fewer of these known, about 20 or less. So they're also poorly understood. This is a picture that Chad and I took at the Lowell Discovery Telescope. And there are a bunch of added images. That's why you see all those dashes. Is they're stars through time. It stayed focused on 2014 OG 392. Centaurs are named after these mythological creatures too, worth mentioning, and they're considered transition objects, which is becoming a really fast, worn-out term. But that means that they're going from between two different classes, right? In mythology, they're half horse, half human. And in this case, the first one was identified in 1927, but they didn't realize it until over 50 years later after the discovery of Chiron in 1977 by Kowal. And yeah, they're also rare and poorly understood. And so as a recap, both of those groups are rare. And so one way we can fix that is by finding a bunch more of them. At least that's the goal. So how are we going to do that? We want to do this with citizen science. And so what is citizen science? Citizen science is essentially crowdsourcing tasks that are either too complex for computers to do, well, and they're also too numerous for one person like me or a small team of scientists to tackle. And it's simultaneously an outreach effort. So anyone who's able and has internet can participate online. We've had about 6,000 participants so far. On the machine learning note, it is possible you can use some of this output to help train machine learning algorithms later for activity detection. But at present, it's not viable. So otherwise, we wouldn't be asking people to do this. Also, because we have more than one person looking at each image, there's less bias as opposed to when it's just me looking at it, it's always the Colin score, and that's the end of the story. There's an image there on the right. This is the kind of image that we would show to citizens and volunteers. Citizen scientists and volunteers interchangeable. Citizen scientist is a term though that's sticking around for a lot of reasons. So we would show these images to people and ask if they see activity or not. But before we actually decided to take a bunch of people's time and ask people to help with this, we decided to do a pilot study. So this is the paper here, Safari, Searching Asteroids for Activity Revealing Indicators. That's with me, Anthony Curtis, Michael Wilmert, Scott Shepard, and Chad. And this shows the dark energy camera, which is this really awesome camera that's in Chile on the Blanco 4-meter telescope. And it's showing there all these different chips. And when an image comes out, it comes out with this mosaic. And so there's a number of chips, 62. There's some others, we won't go there. And this data comes out. This is a pretty color image that's taken with it. In the early version of this pipeline, I should mention, it's a really wide field of view. There's a picture of the moon we took with the BLT when I was teaching. It's 2.2 degrees on a side, so that's like 4 moons on a side. And so you can really see a lot of objects at once. And it's on a 4-meter telescope, so it goes faint. So we take that one frame with these 62 chips or images. They come out as separate images, and then we separate those into different files. We perform astrometry and photometry on them. So this means that we basically solve their positions on the sky and then embed information so that if someone opens the file, it tells whoever's opening it where the coordinates are. And then also the photometry, so measuring the brightness of every object in there, including the asteroids. The next thing we do is actually locate the asteroids, and this is done with Skybot and sometimes JPL Horizon. And so the point of this is to find which asteroids are where in these mosaics. And then the next thing we do is this iterative rejection technique of enhancing contrast in images. So the image on the left, that before is before this enhancement, and on the right is after enhancement. How does it look in here? Ooh, not good. Well, I was gonna say how many people can see the tail on the one on the right. Yeah, that's probably also not great on Zoom. There it is in all its glory. This is 62412, asteroid 62412. It's very faint at about 6 o'clock there between those arrows. So the result from this study is that DECAM data, which is this dark energy camera data, is good for finding activity. And we also found that about 1 in 10,000 or 1 in 11,000 objects are active from this, which is very much a rough agreement, but also an agreement with the other very rough agreements that are out there. I should say too that I didn't know a priori that I was looking at an active object when I flipped through all the thumbnails, and I wasn't the only one that looked through these thumbnails to see if we could find an active object in there. And then subsequently, we also added some automated vetting. So this is a way of reducing sort of that we don't want to have, we'll call it optimizing the citizen science, but we basically don't want to give stuff to people as a waste of their time. And so the very first cut that we do to exclude things that we show people is to make sure that something is actually bright enough to see. And this gets rid of over 60% of the data, 55 to 60%. And so that's about 18 million thumbnail images that we pitch right off the front. I also use some techniques to determine if there's actually a dot in the center. And if there's not a source in the center, then we're not going to show that to people either. How many people can see which one's the asteroid in that image? Like 0. I can't see, so we pitch those out as well. If there's too many sources in the field, especially in that center region, we don't show those. And the last one, there's more vetting, but these 3 I'm showing. If there's too many that are blended in the center, like here we've got 3 galaxies and an asteroid and a star or something like that. And so those tend to also be very confusing. And so rather than passing those forward, we don't send those to the citizen science projects. This is the location of all of those thumbnails that do survive the vetting process on the sky. It says 16 million here. It's grown to 18 million in the last couple of years of vetted images. So this is sky coordinates, declination, and right ascension on the x-axis there. And then each one of these pixels is a 1 degree by 1 degree field, so 1 degree square. And then that color bar shows just how many there are. So some of these have on the order of 10,000 thumbnails in that 1 square degree, and then some of them have very few. And wait, this is my favorite. We're going to interrupt everything for a telegram because we use telegrams in astronomy still, which makes me so proud. And they're by email. Don't worry, they're by email, but they are still telegrams. I put this on a picture telegram. It doesn't actually come like that, but I think it should. But in any case, in 2019, after this last paper was published, working on the project, asteroid 6478 Gault was found to be active. And we decided to try something with our pipeline, which is to go back into all of our thumbnails we're producing and see what else we have of this object. Also at the time, there was like some press that said that the object was exploding, and we wanted to see if that was true. It wasn't. So we found several different activity epochs or different orbits when the object had been active. So there was one in 2013 here shown. So that's Gault in the middle. And all of these thumbnails, unless it's otherwise, the object's in the middle. The white arrow showing the tail. Found more in 2013. There's also one for 2018, not shown. I should add that this is was published as a paper with me and Chad and Jay, Annika, and Ty. We introduced a metric here, which we've been using ever since, which is something I call observability. And it looks like a law on the plot, but we'll walk through it. So on the y-axis is apparent magnitude, and because we're astronomy, small numbers being brighter. That's getting shaking heads from Daniel. So that's the green solid line, is how bright the object is over time, which is the x-axis. Also, this dashed line, which is really what I think of as observability, is how many hours on a given observing night is the object visible, and that means above. It means above like 15 degrees over the horizon during daylight, during the nighttime. And so this lets us see some observational biases that are important, which we'll talk about in a second. So also the very top little Qs are the perihelion passages. So when the object's close to the sun, big Qs are aphelion when it's farthest from the sun. Those stars are the activity epochs that we found in the data. And then that blue pentagon was the current epoch of activity at the time that we found these. And there's also overlaid a histogram that shows how many images we had from each one of those findings. And so when these are coincident at the top, when they're bright and observable for a bunch of hours, that means it's at opposition. There's conjunctions when it's the bottom. And it tells us a little bit about bias, because if we don't find images of the object inactive, it doesn't necessarily mean it was either too faint or that it wasn't active. It just means, the sun was out while it was out, and so we can't see it, for example. Right, so a result that's kind of obvious is that you're most likely to find activity if the object is bright and observable, which makes a lot of sense. And then also we found that you could see from those little stars and the activity compared to the aphelion and perihelion times that there's not really a relationship between when it was active versus perihelion passage. So the result from that is it was 3 times active before, and it's an S-type asteroid, which is known for being desiccated, so very dehydrated. And this is, the proposed before is this idea of being recurrently active because of rotational instability or not through sublimation, and this seems to be the case for this object. So moving along, the next thing I was going to try doing is looking through piles of these thumbnails myself to see what encounters people might have that were going through this experience online. And so I went through different batches. I think the most I did in one day was 120,000 images. I do not recommend that. I'm pretty sure it's like actual damage to yourself. My keys are worn through. I can see through some of my keys. It's great. Don't recommend it. However, I looked at all the centaurs and I found a smudge. I can't even see that on my screen. Oh, actually, it's better on that one than mine. But that looked like evidence of activity to me. So we went and did follow-up, or Chad did follow-up at DECAM, which is the same instrument that these images are derived from, using a program that David Trilling PI'd. And we saw more evidence that it might be active. The 6.5 meter Magellan definitely confirmed this, which was very helpful. And then we were able to do a longer study with the Lowell Discovery Telescope, which was important for a bunch of reasons, not the least of which is we were able to measure colors, which we found that it's on the red side, which is by, you can see this paper by Tegler that talks about these potential bimodal color distribution of red and gray for centaurs. Another thing we did here is to measure how much excess flux was around this object. So what that means is instead of just being a point source, there's something else reflecting light back at us. And so to do this, we cast an aperture around the object as well as another star, or maybe multiple stars, and we compare them to each other. And so this plot here shows the point spread function. So it's how much flux there is radially outward from this object in pixels. And the counts are in arbitrary units because that's fine. And the top line is 2014 OG392, and the bottom line, the orange one, is a star. And so the difference between the two is how much excess flux is being put off by the material that's surrounding the object. This is a common technique used to measure the amount of mass and stuff. So a result here, we found there was about 2 or 4 times 10 to 12 kilograms, or in this 4.3 times 10 to the 5 kilometer coma, which means nothing to me. But since we all lift Nimitz class aircraft carriers, you can relate to those. There's 26,000 Nimitz class aircraft carriers, and the distance of that activity was roughly from the Earth to the moon. So that's cool. But the main result is a new active centaur. So one other piece that we did with this, which was kind of new, a little bit picking from my exoplanet hat, and then combining some other techniques used for water ice to figure out what molecules might be sublimating on this body. There's a lot on this plot, so we're going to just walk it through in stages. The first part is this is the heliocentric distance on the x-axis in astronomical units, where 1 AU is the average distance from Earth to the Sun. And on the top, we've got Jupiter, Saturn, Uranus, and Neptune. So here we're going to add on some lines that shows the perihelion distance with the little q, and aphelion, the farthest from the Sun on the right, big Q. And then where it was at the time we did the study is also a vertical line, which was practically at perihelion. Okay, so now don't panic, there's more lines. So at this point, I do have a disclaimer on here, which is that we make plenty of assumptions when we do all this kind of modeling, including the dust modeling before, really a ton of assumptions, but it's totally normal in our field, and I love that. But single species of ices on a perfect sphere in an airless body in space are actually not at all behaving like when you mix ices. Cranian Sansbury 2000's got an example of why you shouldn't make the assumption. However, as a really rough ballpark, we can determine a few things about how the species would behave if they were single species out there. So these different lines show the sublimation rates in kilograms per meter squared per second. That's the y-axis for the object at different distances. And you can tell that water and the methanol down there, CH3OH, it's not appreciable. It's too cold at 10 AU. And so if they were there, they should still be there because they don't have enough heat without some other energy input to be sublimating. And the sublimation, right, is the process of going from a solid to a gas directly, like dry ice on Earth. And then on the flip side, we've got like carbon monoxide, molecular nitrogen, and methane up there, and those are way faster. And so the other thing we did was do dynamical simulations to sort of estimate how long the lifetime of this object how long was it in this orbit, essentially. And so we found it was like between 13,000 years and 1.8 million years, which, yes, that's like multiple orders of magnitude, but again, it's astronomy, we totally can do that. But, so ballpark, it gives you an idea of the life. And so if there was something that was actually sublimating, and we found again, single species on the surface, we would think it would be carbon dioxide or ammonia, rather than species that should be long gone or species that shouldn't be sublimating at all. So that was a new technique that we tried out for this object. Cool, we got another telegram because those like to interrupt us. And that really is kind of like how they work too, because when a telegram comes, I do just drop what I'm doing and go check out these objects because they're cool. So this time it was 2005 QN173, and it's like 2 weeks before we're launching our citizen science project. So the timing was great. And it was Alan Fitzsimmons found things was active. And then again, the little Discovery Telescope in the picture, this was Henry Shea and Audrey Threeland confirmed it was active with the LDT. And so I went and looking in archival data again, trying to find more images of this object being active. This time what was different is I used many different instruments instead of just DECCAM, more than we're going to list here. And in the end, there were 81 thumbnails, spanning 31 different dates of observation. However, out of all this pile, there's only one that actually showed activity, but it was a really good one. And so this is it was enough to convince Minor Planet Center. So for people that do that, they know that means something. And so there it is with this tail going to about 5 o'clock there. This was an image taken in 2016, July 22nd, by Justin Lang and Alistair Walker. They're awesome. And this was part of their DECALS program. And you can see that there's also an arrow over here. These are pointing also in similar direction. And this is the anti-solar and anti-motion vectors as seen on the sky. So this is where you would predict that tails would appear. I call these predictions, but people will correct me and call them computations. But this is where you know it would appear. It can be a useful tool. So what we decided to do is actually quantify this agreement rather than just sort of eyeballing it, which we hadn't done before. So we came with this thing called wedge photometry. And what it does is count how many photons or counts are in a bin going out from the object at the center. And it goes, in this case, from 5 pixels to 50 pixels. And then it makes a polar histogram going, it's oriented the same as the object on the left. And we do this in a bunch of different sizes of wedges or annuli, actually, but wedge sounds nicer. And we do this from 1 degree to 10 degrees. And the reason for that, you can see from this jaggedness over here, is that we want to try to get rid of some of that noise that's in the background or account for that. And so we found this tail orientation to be 251.3 degrees plus or minus 1.4, which is in agreement with these two numbers of 251.6 predicted by JPL horizons, computed by JPL horizons. Got it. You could also use this potentially for finding activity. So we're excited to try this, especially for upcoming surveys like the Legacy Survey of Space and Time, LSST. We're going to need way more automated tools to actually automate finding active objects. That survey is expected to produce 100 terabytes of data at night, to give you an idea. So we also did thermodynamical modeling for this object. We had done it before with GALT, but we got a little bit more comprehensive. And we model for 2 different scenarios. That's this chi character there, 1 and 4. Where 1 is called a flat slab, which means it's just facing the sun same way all the time, and it gets the hottest there, as opposed to this isothermal case, which means it's rotating fast enough to where it loses, it's uniformly heated on the surface. The result from this modeling was that it was not extreme temperature changes or extreme temperatures. That's what's shown on the plot. There is this temperature on the y-axis in Kelvin, and then the x-axis is time. And so those peaks there are going to be near perihelion when it's warmest, and troughs at aphelion. And one of the important results of this is that water ice would survive on the surface of this body by Colin Snodgrass, 2017. I also mentioned on here that probably not thermal fracture. Thermal fracture is the same thing when, if you've ever tossed boiling water on your windshield when it was frozen, which you shouldn't do. Everyone does that only once if you do it, but I did see my mom do it once. Sorry, Mom. Yeah, that's what happens. Expansion overcomes the tensile strength, and so it cracks or breaks. It's only been seen for NEOs so far, near Earth objects, but we still can rule it out for this one. We also analyzed the activity in terms of the images that we had and if they were clear enough to see activity or not. And so this is the object's position with respect to the sun over time. And we had images at these different times. The unfilled ones are not active. The filled ones that are red means active. And the downward arrow means it was inbound with the sun, and the up arrow means it was outbound from the sun. And so we found this second epoch in this paper we published here. In 2016, there was that current epoch there, and so that means it's been active twice. However, there were data from other periods when we expected to find it to be active, and we did not. And so we're not entirely sure why, if it was imaging issues or if there was something that actually sort of sparked the activity for the 2016 epoch. But that's okay. We have 2 data points, so some statistics. Activity is usually when it's less than 2.7 AU from the sun and when it's outbound. We also will say that our main belt asteroids are like 75% of them or so are C-type, or this carbonaceous material that can have volatiles in it. Shea 2021 et al., they showed that with colors, it was also likely a C-type. So if you take these all in combination, recurrent activity, which is diagnostic of sublimation-driven activity, and it's C-type, then we found it's likely sublimation-driven activity. And that would make this the 9th main belt comet, which is a subset of active asteroids that only orbit in the main belt, and they have sublimation-driven activity, which is characteristically at around perihelion and maybe not elsewhere in the orbit. All right, so moving on faster. We're at Active Asteroids Citizen Science. So this is actually launching the project itself. So this happened at the end of August 2021. Oh no, there's subtitles. It's going to be fun. There we go. So this is with myself and Chad and Jay Cuny, a student worked with me here for 2 years. Will Burris, who's in here, and Will Oldroyd, who's online, and Henry Shea, who's also online. And this is the Active Asteroids project, which is now a NASA partner project. It's funded through the NSF GRFP that Chad mentioned for my talk. You can go to this URL, activeasteroids.net, and you can participate yourself. So real quick introduction to the project. If you land on it, you will be introduced first with a tutorial. This just tells you the sort of basic scientific motivations of what we're doing, explains things like a coma, because a lot of people have heard of tails, but not this cloud idea of there being a cloud of dust or material around an object. And then we give some activity lookalike examples, such as this number 4, which is a galaxy parked on another galaxy parked on an asteroid, which happens a lot, which may look like a tail, but it's not actually a tail. There's also a field guide that's available at all times. There's many different sections of this, but if people come across something they find interesting, they can look it up. This example here is cosmic rays. These are high energy particles. They come across on the camera and they bounce around and they make these black lines. And so we explained those aren't actually in space and they're definitely not an activity tail. So the overall experience is to identify whether or not there's activity. So it's just a yes or no question. Keep it really simple. I don't know how many people see a tail here going down. Yeah, I'm by that. And so users can do things like invert the image or rotate, do some different things. They can favorite them and collect them into different albums. And then also you can, when you're done, you hit done, or you can do done in Talk. Talk is an online forum, chat forums essentially, where people talk about stuff, but they can also post these images there. And that's really cool because it turns out that was a pathway for discovery we did not anticipate, because all of the initial discoveries actually came this way before classifications were done. So like here's an example of an object that is active. We haven't published this yet, but if you have a telescope that can get to like 31st magnitude, let me know. Yeah, so that one's going to be a minute. I also created an activity training set. So I looked through thousands of images of comets, active asteroids, active centaurs, and classified them by my own scale. And the ones that definitely had activity, I pulled those out and we made a training set. And the main purpose of this is so that as users are classifying stuff, if they get these shown at a decreasing kind of interval, depending on how many images they've ever classified, and you get feedback saying like, yes, you found something that's active, or no, you didn't. And this is important for a couple of reasons. One is it helps people learn about it. And then second, apparently people can sort of second guess themselves after a while if they haven't seen something active. And also it's fun to see active things. So the overall process, this is in a nutshell. People classify objects and they come out as records, which we do analysis on. Talk about that in a second. There's also this talk pathway. Between those two, we get different candidates. There's of course overlap between those two quite a bit, because if it's coming out and talk as active, good chances are that people are classified as active. And so then we have these pilot candidates, and then we look through those ourselves and vet those. And the most interesting ones, and which is actually a pretty high percentage, we do archival investigations for all of them. A great thing about archival investigation is it's instant gratification. If you find other images of activity, it's just like, great. I mean, not done, like we still want to study, but it's a huge, it's really exciting. And then telescope follow-up, and then to science. Just a quick moment to just also add a comment about that. I mentioned that really faint object earlier. We anticipated some of this, but there's actually quite a few things that keep us preventing us from falling up on an object. When the image was taken, it may have been at perihelion, and now it's at aphelion and far away. It could be, only up while the sun is up, so we can't observe it. It could also be out there. It's amazing how many of ours turn out to be fainter than 26 magnitude now, and so that's also a little bit difficult. And so we have quite a pile of definitely active objects, but that we definitely can't go after right now either. And so that's been an interesting exercise. On the other hand, we also have some that we can and do, and talk about that. When I say classified, this is the kind of statistical analysis that comes out of these. So 15 people look at each image to reduce the bias and to get to an even amount. This is also better than just me, because then it's biased by Colin. And we wanted to see if people could really identify activity. This was kind of a watershed moment, made me a little nervous. And in the training set that you can see on the left here, the majority of people saw activity in these images, which we know show activity. And on top of that, the slope's pretty steep. And so it is a good indicator. We want everyone in that 100% bin, but this was a good sign. And then on the flip side, since most of them do not have activity, most of the people did not see activity in any of the sample images that we wanted classified. And so this was also a big relief. I said 15 classified, it can be more, and that's why there's this weird kind of saw, this jagged saw appearance to the plot there, because it can be 16 if two people happen to be classifying at the same time. So the result there is that people can indeed distinguish between activity, although frankly, we already knew that because we already had discoveries falling out of the talk forums even before we downloaded our first classification set. As promised, some teasers. So we've got on the far left there is an active asteroid, and we're working on this with also with Will Burris, because we are refining those statistics greatly. The ones that I showed on this previous page, there turns out to be a lot of room for improvement on this. For example, if someone has done classified 1,000 objects and they always click yes, it's active, that's a red flag, and so we can account for that. But that's an unknown active asteroid there, so yeah, don't take pictures, please. And none of these are published yet. Second one, which we're hoping to submit tomorrow, no, within a week. That's another paper that's coming out. This is a new quasi-Hilda. This is a kind of object that's near the orbit of Jupiter. And it's not exactly in 3-2 resonance with Jupiter, but it's close. The third one there is another main belt comet that Henry and I need to get together and publish that thing. And then the last one is TNO. That's a paper I'm meeting that's with Will Grundy and Jay Cuny, Audrey Thurin, and others. And this just fell out when I was looking through all these thumbnails. I kept seeing these co-moving dots, and it turns out they're widely separated binaries, and so that's cool. And there's options maybe to do citizen science around some of those as well. But in the meantime, there's this one, and there's more. So I'm excited about that. So in summary, we built this pipeline. It runs daily with LSST kind of in mind to be able to work with big data. And we extract these thumbnails and for showing to people. We also do all this, it's a relational database. We link this stuff from Horizon to other places so we could show those plots like with the apparent brightness to assess things. 4 papers so far that just fell out of preparing for this project. And then we have several more, 3 that I'm actively writing and 1 very close to being out the door. And then the citizen science project that's live, please check it out at activeasteroids.net. And anyone could participate in this. There's data to be done right now. And we have a bunch of discoveries, a lot that are waiting to be processed. And so far, 2 million classifications done by 6,000 people. We have this comet test data set that's going to fall out that I've promised will give people soon. And 5th manuscript I just mentioned. And so in the end, the foundation is in place for finding many more active objects. And we found some already, and we found some made discoveries along the way. It helps advance this idea of volatiles in the solar system and learning more about them, but we hope to do much more. I also want to acknowledge some citizen scientists. Everybody in the project is important. Also our moderator, Elizabeth Nathan, we would not be able to do what we're doing without her. Our top classifier is Michelle Mazzucato from Italy at 150,000 out of those 200,000, and probably more. I just haven't checked lately. And then these super volunteers, I've got a bunch of people that are doing a lot of good work, and everybody on that list classified at least 40,000 thumbnails. So that was great work. Thank you very much for that. So this last bit is acknowledgements. There are dozens of pages of acknowledgements, I think, in my dissertation, so I'll have to point to that. But just really quickly, in memoriam, 2 people that I really wish could have been here that aren't. My friend Jean Beauty passed away last week. Nadine Barlow also, I wish she could have been here. Also going to mention that we are on former Native American land here, and especially in our telescopes. And you can, with very little money, help and a long way on the reservation, especially Southwest Indian Relief Council and the American Indian College Fund. It's amazing, $10 a month, how many meals, like 900 meals that provides. It's a big deal. So please, I encourage everyone to check that out. I'm going to thank my partner, Mark, who's online, and my family, especially mom and dad, for all their support to this, and my committee, Chad, David, everybody on my committee, and everybody else I've worked with. Like I said, there's too many to list. So thanks again very much. I'll leave the slide here. This is your job. I guess so. I don't know. Yes.
All right. Thanks, Colin. Very interesting. Any questions from the in-person audience here? Oh, that's just Lisa.
Oh, I have two questions. First one, you mentioned a little bit. So out of the 30 active asteroids, what's their relation with types? So one is the one you just.
Yeah, so Gaul was an S-type, and it's yes. Let me repeat the question for the everyone that's on Zoom. So Lisa was asking what sort of, I guess, the proportion of S-type and C-types there are out there. That's a great question. I don't know. I just know that there are very few of these S-types. That of the 10 that have been found to be recurrently active in the asteroid belt, 9 of those were from sublimation, and they're not thought to be S-types. And Gulp is the only one that's thought to be an S-type. And there's a handful of other investigated ones that are thought to be active because of rotational instability, so spinning too fast, breaking apart, landslides, tossing material off. But they're definitely, I would say, in the minority. S-types the minority.
Oh, the minority.
Yeah. The C-types. Yeah.
My second question is, what's the difference? Is there a definition of active asteroid versus main-belt comet?
Yeah, so main-belt comets are a subset of active asteroids. It's a fair question. There's a lot of confusing terminology here. I did manage to not use the acronyms, which is amazing. But so main-belt comet is an active asteroid that orbits. So there's like 30 of those, but only 9 main belt comets, and those exclusively orbit the main belt. So the first active asteroid I showed, 4015 Wilson Harrington, that's actually a near-Earth asteroid. And there are a bunch of other near-Earth asteroids that have been active and other types of objects, and so those are not main belt comets. So the main belt comets are defined to exclusively orbiting in the main belt. They also can't cross the orbit of Jupiter, which we didn't get into because I don't believe in doing equations like this. And they need to be recurrently active because of, well, they don't have to be recurrently active, but they have to have shown be active because of sublimation-driven activity, whereas there's many other types of possible causes for activity out there. The main ones being rotational instability and sublimation, but it has to be sublimation to be a main belt comet. Yeah, and that's preferential activity at perihelion, and a lot of them also don't have activity anywhere else in their orbit. So it's like they turn on and then turn back off. So it's a subset of active asteroid.
Questions?
Yeah, I saw Jeremy Cooper. Wow. Hey, how you doing? Long time no see.
Hey, great talk. And I'm really interested in the citizen science angles. Really 2 questions. One is you mentioned using your own personal research to make a training classifier for possibly machine learning. Have you considered turning that on, giving your top classifiers and using their output as a training set? Maybe you did that and I had missed it.
We have thought of it, and no, I didn't say it. For the audience, the question was, have we thought about using our top classifiers only as being to produce a training set for activity? We absolutely have thought about that. I think one thing that we should be clear about is that there is no human subject involvement in this part of the project, right? So the data, we're not assessing the people per se, that being said, we absolutely have looked at this angle, and it's something that we're looking at in terms of also just figuring out how other people are doing in comparison. So yeah, we're definitely looking into that.
Cool. And my second question is solar output activity, things like geomagnetic storms, I guess that's Earth-based, but sort of solar wind, does that ever have any effect to correlate with the sorts of activities you're seeing? Is that something was considered or something ruled out, ruled in?
That's a great question. So the question was, is solar activity in any way connected or correlated with active asteroids or other activity in the past? I will say that that people have tried to connect those to each other. I'm not so sure that it was actually, I'm not sure how successful it's been. Let me just say that diplomatically. And then the other thing is that we have seen the instances of the solar wind mattering for as a secondary mechanism. So like on the moon, when the Apollo astronauts landed there's like levitating dust and what that's about. So you can have this electrostatic lofting even on a body with gravity. And if you have solar wind or something like that that can sweep it away, then you could make activity. Whether or not that can be on a scale that we can detect from Earth is another question. Several of the active asteroids are out there, such as Bennu and arguably Ceres. I mean, the only reason why we know they're active is because we have a spacecraft at them. And so we might be able to see these kind of more secondary effects through that mechanism. But people have tried to connect solar activity on a broader scale with active asteroids, active centaurs, and other active objects, including comets. And it's more obvious when a comet gets close, but in terms of active asteroids and active centaurs, I personally have not seen a conclusive evidence yet. It was a great question. Thank you.
Great, thank you. Passing it on.
Maybe let's do a couple more questions. Anyone,
Yeah, we're at 2.
Anybody here in this room? Yes?
Yeah, so you kind of actually at the beginning of your talk about how you're interested in the origins of volatiles. Has anything come out of the citizen science or of your research like centaurs that relates back to that question, or relates back to where volatiles in the inner solar system came from, or kind of how that evolution happened?
Yeah, so repeating that, the question is, from the work that has been done, including through citizen science, have any active asteroids or active centaurs been connected with origins of volatiles in the solar system? That's my understanding, right? Roughly? Okay, Audrey says yes. So I would say the answer is I'm not there yet. And I don't think that we're there yet with the numbers that we have. You also said inner solar system. So a lot of people thinking about origins of Earth water, think about it in terms of the inner solar system. But we want to find more. I mean, I think at some point we'll be able to connect like sizes and volumes and think about what could have been delivered. But I think right now, I mean, not that it doesn't stop people from trying, but if we only have 20 objects or 30 objects, it's a pretty small number. So not yet. I'm looking forward to that though. I don't know if there's any on chat because I can't see chat.
Oh, you can't see the chat?
No. I only saw Jeremy's hand wave up because it pops to the top somehow.
Let's see in the chat. Maybe another question from the audience. If there's one.
Oh, great job.
Thanks, Aaron.
Presentation. I was just wondering I liked your wedge with photometry approach. How do you calculate the number of pixels radiating out from a single point? Are you using automation there?
Yeah,
and if you are, is that not applicable to the citizen science project? I mean, does that show? It seems to show pretty good agreement of where a potential or where activity is happening.
Yeah, I agree with that. So rephrasing for Zoom, Aaron's question was, have we tried applying this wedge photometry on a more automated level, including stuff for citizen science? Is that the question? So I would say no, although my habit is to write all my code so it can run on monsoon and just do a bunch of computing. However, in this case, I said 5 to 50 pixels, not an accident, because that does not account for it. That leaves out the stars that are in this field. And at some point, if I had time, I would do some nice deep blending stuff or some subtraction, looking for outliers. That would be a great project for an undergrad or somebody to do in the future. Because yeah, in order for this to be useful in automation, it needs to be able to deal with extraneous sources and outliers. I dealt with some of it in the noise in the interior with those 1 through 10 degree bins to be able to try to toss out some of that noise. But like for example, in those OG images from before 2014 OG 292, it's amazing how many of the ones that we have, even though it wasn't a very dense field, they still ended up on top of stars. And so that would require some kind of deep blending to separate them. And then if you have stars that are even at all nearby or other image artifacts, you'd have to automate removing those as well. So we haven't applied those yet. But your other question about the citizen science part, I think one thing that would be ideal at some point, especially for LSST, because of the volume of data, is to use all of these techniques somehow synthesized to try to find metrics that bump up the probability that there's something active in that image and use those as our selection criterion for what we submit to citizen scientists. So that is on the radar.
Great, yeah.
Thanks, Aaron.
So it's 5 after, so I guess if you do have additional questions, maybe ask Colin later.
All right.
Or type them in the chat.
Thank you.
Or send an email.
Awesome. All right, thanks everybody.
Can we give another hand to Colin?
And thanks everybody online for joining. Much appreciated.